Lecture 25, solid state. So in this lecture, we'll talk about the unit cell, the molecular solid, covalent network solid, and metallic solid. All right, so in a solid, basically, they're crystalline. Okay, so there's two types of crystalline. There's amorphous, where we have a random arrangement of particles, so basically it's very unorganized, things like that. And we have a crystalline solids, which the units are very organized. Okay, so like sodium chloride, sodium chloride, sodium chloride, sodium chloride. Very nice, very neat, very beautiful. Okay, compared to the amorphous structure. Now we can tell if it's amorphous or crystalline structure by how it breaks. So if a compound breaks, like say here it says glass example, right? Okay, if you notice when you break glass, it breaks into many different sized pieces, big, small, different shape. Because why? Because the structure is very unorganized. While in crystalline solids, it breaks very nicely. So I mean, in a crystalline solid, if you break it, it will be like a straight line. It will break like a straight line. Okay, so it's very neat and very nice. So within a crystalline solid, the simplest version of the crystalline solid is basically a unit cell. It's the smallest repeatable unit. So in things like sodium chloride, like salt, we would have sodium chloride. That would be the repeatable unit, okay, or in all direction. So we're going to talk about three types of unit cell. We're going to talk about simple cubic cell. We'll talk about body-centered cubic cell, and we'll talk about face-centered cubic cell. So the only three you know is this. There's a lot more, but we're going to focus on the easy stuff now. So here's a crystal lattice, let's say sodium chloride. Okay, so you have sodium chloride, sodium chloride, sodium chloride, and so on and so forth. One of the repeating pattern of the box right here is a unit cell. Now you notice the unit cell has the atom on the corner. So notice there's 1, 2, 3, 4, 5, 6, 7, 8 box. Okay, I'm sorry, 8 atoms in the corner of this box. So within that 8 box, you have the 8 pieces of the atom. So if there are 8 corners, and each of them basically gives you an eighth of an atom, so in a unit cell of this simple cubic, you may only have 1 atom per cell. So you put them all together. So a simple cubic, you have basically 1 atom per cell per se. So if you look at only on one face, you notice that this is the radius of the atom. So this is the radius, this is the radius, this would be the center of the atom right there. Okay, so that's your radius. So in a simple cubic, you know that the atom is made up of basically 2R. 2 radius here, 2 radius here, so the volume would be both of them. Okay, so remember, the density, which is P here, this is density, is equal to mass divided by volume. This is called a body-centered cubic. So if you notice in the difference here is you still have the cubic on the outside, but notice there's an atom on the inside. So in a body-centered cubic, you will need to remember that there are 2 atoms per cell. One, the whole atom, and the other are these eighths that combine to create 1 atom. So if we cut it diagonally, you will notice this is the center atom, the whole atom, so it's 2 radius, because remember that's diameter, and we have the radius here and the radius. So the volume with this would be then basically radius and radius, okay, or the diagonal here. So you need to find the diagonal here, then you will be able to find the radius on this side, okay. So cross section again, this is going to be 2 unit cell. Here we have a face center. A face center means you have your 8 for the cubic, but instead of having 1 atom in the middle, you have basically 2 atoms on the side. So you have 8 corners with on each, you have 6 faces, 4 on the side, 2 up and down, equals basically 4 atoms per unit. Okay, so this is face center. For face center equals 4. So if you look at face center, so this is the side view of one of them, you see that it's very similar to that of the body center. Okay, so you have basically 2 radius. Okay, there you go. Now let's talk about molecular solids. Molecular solids are held together by intermolecular forces also. Okay, but they are weak. They're really very weak. Thus, they're usually soft and they usually have a low melting point. Now, here's an example of molecular solid. Okay, so this is a compound. This is an aldehyde. Okay, and notice that they're all basically on here is just H bond. Here you have hydrogen. You have a hydrogen bond on this side. So basically, you have this end that is nonpolar, and you have a little polar part right there. So the bigger this end is right here, the bigger this end is, the nonpolar this thing becomes. Okay, the more nonpolar it becomes. So here we have also a double bond in this compound. So this is fat right here. This is saturated. Saturated means there's only single bonds on the carbon. Okay, this doesn't count. Here's unsaturated because there's a double bond on this double carbon, which means something else can go. That's why we think unsaturated fat is better than saturated fat, because there's somewhere that another atom can come in and actually break this apart. Okay, here there's no chance for another atom to come in, so this type of bonds, this type of compound doesn't break apart very easily. Now, covalent network solid. Covalent network solid is held together by something we call a network of covalent bonds. Okay, now these, because of it, it becomes very, very strong. Network solids are very strong. Thus, diamond is a network solid. Very hard, very high temperature. Okay, they bond together in sp3 hybrid orbital. Okay, so they're very strong. Network solid are very strong. So here's graphite. Notice the network right there. Okay, all the network on the network. The thing about graphite is it's only an sp2. Okay, it doesn't have that extra down to connect, and because of that, they lies in layers. Okay, so in layers. So the thing is, side to side, it's very strong, but up and down, it's very weak. That's why when you basically write using a pencil, which is graphite, this layer just gets stripped off, strip off, strip off, and that's why it stays on your paper as the pencil mark. Okay, so there it is. So as you write, this layer gets stripped off, strip off, strip off. So they're strong sideways, but not horizontal. Okay. Here's another network solid, silicon oxide. Okay, the empirical formula. It's very strong. Why? Because it's a network solid. Okay, because Si is very similar to that of carbon. Okay. So general characteristic of a network solid: it's very hard, very high melting point. Great things like diamonds and stuff. Then metallic solid. Metallic solid is not a covalent. Remember, it's more ions traveling over the place. Okay, so they're pretty strong, but they're not as strong as network solid. Okay, so bond strength will increase as the number of bonding electrons increase. So the more electrons you have for bonding, the stronger the bond for the metallic solids. Okay, we're not going to use much on metallic solid. So here again, the metallic bond, we talk about the seas of electrons. So the electrons are moving around. The more electrons you have, the stronger bond this will become. And that's it for this lecture.